Let's see.
Oh yeah, let me sign into Twitch. Twitch people.
Here we go. I think we're on. Let's see. Yep. Whoop.
The Twitch everyone is complaining about? Oh no, it's Reddit.
Sorry.
Oh, the Reddit is everyone is complaining about Reddit at the moment. But I got confused. I thought people were complaining about Twitch. It's Reddit, isn't it? But people,
I think Twitch
like the r/Haskell was shut down for several days.
Yeah, I think the CEO has gone on a tangent. Let's just.
All right.
That's a nice way to put it. Yeah, and yeah, but Twitch is also having some issues.
Oh, okay.
Nothing compared to the Reddit situation. They're just losing some streamers to new startups that are paying the big streamers to go over. So just normal business, nothing. Yeah.
Are we waiting for our contract then from one of these startups?
Yeah. Yes.
You don't settle for anything less than like a few million. Yeah.
They're gonna really like roll out the red carpet.
But think of the prestige.
Yeah. I can't wait. Just 999,957 followers to go, and then yeah, we're there. So let's continue streaming about something that almost no one knows about or cares about.
They should care though.
That's an interesting debate. If they should care. Like, I don't know. Yeah, maybe one day, maybe.
No, I think they should care.
Yeah, maybe one day politicians will care about proofs. We better create some corruption tactics before that'll happen. But once we have a corrupt tactic, I think we can convince them. So we've been working on like a tactic for lists for a while now, and what we want to do is kind of combine a bunch of alternative tactics that we have, and then repeatedly run this tactic over and over until it hopefully solves the goal, or at least like progresses as far as it can through our proof. And so two of the tools we're going to need is this this first thing, which is basically just saying run this tactic first, T1, and then if that doesn't work, run T2, and if that doesn't work, run the next tactic, and if that doesn't work, run Tn. So in Coq, this was like a double pipe character, but here you write first out, first the word, and then a pipe, and then all the rest you can delimit with pipes. And I think it's just a way because of how like the syntax is easier to extend if you have a keyword at the start in Lean. I think that's the reason. On the other hand, it's kind of a nice readability thing. We go first this, then that, but yeah, I guess we can debate about.
I thought it meant like the first. It could mean like the first match, the first tactic that matches.
Mm,
I don't know.
yeah.
Who knows?
I like that too.
It looks a bit confusing though, because first looks like the name
It could
of
be a tactic.
Yeah.
Yes.
Yeah.
That would be, so we should definitely have a tactic called first. Just to make this really confusing. First pipe first.
Or second would be good.
Oh, second, that would be amazing. First pipe second, pipe third.
No.
No, we're gonna drive Walter insane.
Second is definitely the tech. So I think it goes first or second or minute.
Ah!
Yes.
We can generate some really horrible things.
Yeah, with every pipe you should change the unit you're being sequential in. So maybe it's first or second or hour or there, like there's something. Yeah, cool. Someone can work on those tactics. But we'll not. I'm gonna say we're not gonna do that.
You're gonna deprioritize this.
Yes, definitely deprioritize this. So we're gonna need this or tactic thing, and then the other thing is we need repeat, which just repeats this list of tactics over and over until none of them does anything, because repeat will stop once. Like repeatedly applies the tactic until it fails. So given this list, if none of them can be applied, like we just stop. So basically, like if you have some theorem, then it's like, oh, I found I can apply this I can apply this theorem, and now I can apply this other theorem, but now actually the first theorem is useful again, and because of this or, it will just repeatedly apply until it runs out of anything we could have thought of to do. And that's cheaper than thinking. So
yes,
with our brains. So
that's the point.
Yeah.
So Walter, could you show some examples of the tactics, the use of the tactic we already have? Because Gregor has been away for a few sessions.
Yes,
and he's also not so familiar with tactics themselves. So
yeah.
Here we go. We've got piles of examples.
Yes.
Of everything. So
yeah.
Let me just show you how they're used first. Like,
and also, like, I haven't been doing this for a while, so that's just a good refresher.
Yeah.
Okay, so this is a tactic called list empty, and cool. And we have this. Actually, let's show you. We've built our little helper tactic library called Ltac, and it does a couple of things, but like, so just know all of these things aren't like built into Lean, but we've based a lot of these things on how Coq works and how its language Ltac works. But let's.
So we are basing all of this on this quasi quote or a metaprogramming library called Q or something.
QQ as well, yeah. So a lot of QQ and a lot of our Ltac. That's the and QQ is built in. So that's this little Q here. But yeah, let's start with like an example, and then but that's the scope of what's going on. So
what does the Q do? Yeah.
I'll totally explain that right now. So
okay.
This list empty is like a collection of tactics about empty lists, right? So if there's like an empty list somewhere in the theorem, it's probably going to know what to do with it. So we get the goal, like what is our goal? What do we want to prove? And then we do a pattern match on the goal. And we say like, is the goal something where X is not equal to the empty list, or something is not equal to the empty list, but that thing that's not equal to it is a list const to another list, element const to a list, sorry. Because then we know the list is not empty, right? So this is just kind of obviously true. And we have a theorem for that, so we can just say run the tactic and apply it. And this Q library is the thing that enables this pattern matching on the goal.
Okay.
It does a lot more that I don't actually understand. I only needed to do the pattern matching.
Yes.
And but it is much more the pattern matching is like just scratching the surface of what the Q library can do. But for my use cases, I only need this. It's more of a kind of meta programming thing for Lean as well. Like it's I don't understand it. I think more examples would be useful and kind of motivations. But it's very powerful library. That's the point.
There's also like a kind of reflection library.
Yeah.
Okay.
Yeah, so in this case, it's just lifting that expression into syntax. So the thing you're matching is actually, you're matching on syntax, and then the thing inside of the tilde Q is like it's like a Lean, looks like a Lean expression, and this tilde Q lifts it into syntax.
Yeah, and
then the backtick does the opposite.
Yes. We never use the backtick inside the queue. But I think like Gregor is right, like this is actually a reflection library that is actually, I'm gonna guess that is exactly what it is. And we're just using pattern matching in the reflect library. And then these dollars, I think the dollar is the escape, Paul, and not the back. And it's a weird. Maybe it's not even the escape. Maybe but it's pretty weird because you can give these things names, but where we need to let me see if I have an example. Oh yeah. You can if you say this like x and x and x's, right? I would assume these two x's are equal, but no, it's just the last x that gets the value. So this one would just be ignored. They're not compared. So if you want them to be equal, you have to do like a comparison check here. You go like x, y, and then check if x is equal to y. No, so we just have to keep that in mind because in Coq it kind of does that for us. So you do a pattern match and then you decide which tactic to apply. That's what's happening over here. And then you can do it's like creating holes that can be filled with anything. Well, any kind of variable name. Yeah. But we're not. So we're capturing x and x's. So is there places where we actually use that? I feel like there is. I think we've avoided it. Yeah, we've avoided it very well. Yeah. So I don't have an example. Sorry. Yeah, we just check, is there such a pattern, and then we apply our tactic to the goal. Or we can also get all the hypotheses, and then we can loop through them and check, oh, is this hypothesis, does this hypothesis say that an empty list is equal to some list that is const with some element? Because that cannot be true, so just try contradiction. But we can use the hypothesis name, like yeah, we use the hypothesis name to apply tactics in an hypothesis that we've pattern matched on, but we haven't used these X's or the pattern matched variables to do any more specific targeted applications. So it's not very precise, let's put it that way. Like, we apply theorems to the goal or to a specific hypothesis, but in that hypothesis, many things could have matched. Like for a rewrite, for example, like here at the end, we just try a bunch of rewrites. And we just go, well, we could have pattern matched, but rewrite already does the pattern match for us. So let's just try to pattern. Let's just let rewrite do all the work.
So if there are multiple possible matches, it just takes the first match and captures those. Okay.
Yeah. So that's where we're very imprecise. Yeah, it is a bit of a throw the kitchen sink at the proof and hope something sticks. And yeah, we might need to factor these out. I'm just thinking, like, these will all succeed, and we need our tactic to be able to fail. So we'll move these around. We'll need to put this tactic, this list empty, into an OR, and we need it to be able to fail for the repeat to stop. So we will move these somewhere. Yeah. So
just one more question. What does the backtick do again? Did you say that already?
No. Okay. So in this case, the backtick paren tactic slash pipe says start tactic notation. And then we can write any tactics in here. So, and the run method, the run function takes this tactic notation and executes it.
Oh, okay.
And this run is part of our Ltac library. Just like get go prop. No. Okay, this one is part of our Ltac library. And get hypotheses is also part of our Ltac library. Just very small convenient functions that like changes it to use the queue, and yeah, this makes it slightly easier to use. And then we have one more thing, apply in, which is say like, okay, I want to apply this tactic inside this hypothesis. And then here, interestingly, I don't have to say which notation it is. I can just say it is a notation. And apply in knows that it is expecting it to be this T syntax notation, T syntax term notation. And yeah, it would be nice if I can figure out how to remove this tactic also for run, so that because kind of then I would change the function name to run tactic, which would be more descriptive, but I don't want to type run tactic.
Yeah,
That's-
makes sense.
yeah, but yeah, maybe one day I figure out how to change run to always take tactic notation, and because currently run, yeah, it's doing kind of the same, but apparently, yeah. So yeah, we'll see one day, or not. Yeah, but yeah, we can apply in a name, and we can also make new hypotheses. So give it a name, but which is based on the previous name, and then say like, okay, given like this hypothesis, take the left of it and create an hypothesis name that is just left, so that we can go around. So this is like for a conjunction, and you just want to take the left and right and go like, okay, if we have an hypothesis that is a conjunction, just give me the left and right as separate hypotheses. I don't need the conjunction.
Yeah,
because we needed to do this quite a lot. So yeah, I think that's it. I think that's everything. So good. Everyone happy with the refresher?
yeah, that doesn't look too bad.
Yeah. Yeah, it was a little bit of a pain to get here. But now, yeah, now it's just pattern match, apply tactic, pattern match, apply tactic. And yeah, we're just gonna have this big library of pattern matching and applying tactics, and then a bunch of rewrites at the end. And then we just want to OR everything, and yeah. But before that, we created this little tactic called list application uncons. So if you have something like this, where you concatenate two lists, then you know, like, okay, either y is empty and z is equal to x cons y, x cons x's, or see, oh no, if we go to our lists, because it says it better, but like writing this in a documentation is kind of hard.
Yeah.
Basically, otherwise there exists a y's such that y's might have the x in it, and then z's has got the rest. So you basically trying to like say, okay, either the first list is empty, or like, yeah, actually that was really badly explained. This theorem explains it better. This example application. So you say like, okay, x's and y's concatenated gives me x and y. So either x is the empty list and y's is xy, or x is x and y's is y, or x's is xy and y is the empty list. And you just want the tactic to just give me all these alternatives, and then I can just finish the rest of the proof, because I can just enumerate these possibilities. I don't need yeah, to wonder what x and y are. So we can try to use this theorem, this tactic, to prove this proof. That's the word. And we can look at like how we did that in Coq. Yeah, so here we have the same theorem that we had that we have in Lean already proven. And here we have the tactic for it that helps us apply it. And here we have the proof. So we wanted to be something where you just go uncons, okay, it's the left side, it's the right side, and let's yeah. Let's see what happens here. So we just introduced our hypothesis, and then we can apply list app on uncons on this. And we see our hypothesis is split up into x equals the empty list or the other thing. And now yeah, so now we can like look at, given this goal, we kind of want to go, let's first look at the left side because it's a bunch of alternatives, right? We basically want to write 3 proofs. So I think we need some way to say we only want to look at the left side. I think this is like a pattern match. I can't exactly remember. Is it cases? No. I think there is some thing in the document.
Already forgotten.
Yeah,
Already forgotten this.
I think this, or okay, no, that's the hypothesis. I want to do cases on the goal. What if I say apply or dot? Okay. No, okay, then oh yeah, exact h dot left. No. Okay, yeah, so it's not a okay. Okay, so I think if we do cases on h, then we can go if h is left, and then we can try to prove the goal on the left side.
Right, yes, because if it's left, then we can do the left and the goal, but if it's right, then we can't go left. Yes.
Yeah. So if we do this, yeah, okay, good. Okay, yeah, so now we know this, and we know we can only prove the left side.
Yeah.
And now if we go apply or dot left, then it is exactly the assumption. Okay, good. Whew, okay, it's been a while. Now we know this.
Oh, I'm remembering this. Now I'm remembering the last time when we had this underscore PYS and we didn't know what type it was, and we had to. Do you remember that? And we had to write. We like wrote the type out in a comment, but you can just hover over it to find its type.
Aha.
Yes.
There.
But we couldn't figure out like where this was. Now I remember. Yes.
Yeah, this is true. Okay, good. Thank you. I don't think we were.
Because I forget what we're doing. I think it was writing the proof, and we were keeping track of this type in a comment. And we're thinking like, well, how would you know that what the type was?
Yes.
And you have to hover over it to find it.
Yeah, because we have to provide this exists.
Yes. We have to say exists some wise such that proposition holds.
Okay, I'm gonna copy it again.
Yeah, we need to put it in a comment.
Yeah, I'm just gonna put it there. And why is, oh. Okay, wait.
What does this mean?
Yeah, wise is just a list. I think p-wise is this function, Yeah.
Well, what I can't remember is that, so the exist should be a pair of something and then a prop. So
Yeah, so
what is this underscore p-wise?
Oh, yeah.
Because we've got the proposition on the right-hand side of that comma. We've got that exists wise prime, and then we have this underscore p-wise, and then we have the actual proposition of the pair on the after the comma. So is this saying? Oh, but then this underscore p-wise doesn't appear in the right-hand side after the comma.
Oh. Yeah. No. I agree.
So I can't remember what this existential quantifier.
But I do know that y is prime should now be the empty list. Because then y's would be okay here, right? If y's prime is the empty list, then we have this, which means this, and this, and that's what we want. I don't know how to do that. And I don't know how p-wise fits in to that.
Isn't it maybe like a constraint on the y's prime, because it's a function that does something with y's prime? So we have to show that there exists y's prime such that there also exists a function that does this thing with y's prime, and then the rest.
Yeah, and that's also, I think, why the underscore is there. The parameter is not important. The resulting property is. Like,
yes.
Like you. Yeah.
Then so we can try then.
You only get this one out. Yeah, you only get. No. But let's go look at exists. Here we go. Command click. Oh, so good.
So this exists as an elimination. So exists.ln.
Okay. We're okay. Let me copy this as well, and then.
Yeah, because that's the introduction. But
Yeah.
we've already got an exists. We need the eliminator, I guess.
And then you said elem. Exists dot okay. Just copying everything here, so we have. Oh
yeah.
And maybe I don't need to comment it out. The syntax highlighting might help.
So if we had something in the goal, we would use exist.intro to create an exists.
Yes.
Because it's a hypothesis, we need to use exist.intro elim capital H.
Actually, I think the reverse.
Oh,
If we had, no. Yeah. If we had
we
it
do
in,
exist.
we would use,
If we had it in the goal, we use intro.
I think we would then use eliminate.
Oh, okay.
Because then you break it up. Because you have it in the goal. Like you work in reverse, right? If you have it in the goal, and if you have it in hypothesis, then you can create it.
No, isn't it the other way around? Like, why do we
thought
have
it
to
was the other
create
way
it when we
around.
have it already?
Yeah. No, you're right. Yes, I'm wrong. Yes, good. You're both right. Okay. Yes. So we have it. So we can use elim. Yes.
Yeah. So you call, so you say elim, and then elim gets a function. Yeah, so if you just say like exist.elim h, capital H,
Okay.
I think. And
Maybe
then,
apply.
yeah, so then we get this function.
Oh, this applied it to the goal. Oops, that's not maybe why. But maybe that's fine. I kind of just wanted have.
No, because if you look at the type of exist.elim, it gets a function with
Yeah.
because what you were doing, we're eliminating the pair. So this H is a pair of something and then a proof that the property holds. So I think the exist.elim, you need to give it a function which accepts those things. And you get to construct a.
Okay, but so if you pass it something.
Yeah, we just look at the type.
So we passed it the.
They're all implicit, aren't they?
Yeah.
I'm not sure what this means. Maybe this is the wrong.
No. Okay, here's another parameter. Yeah. Here's the parameter we passed.
Yeah.
This one. We only passed in this one.
Yeah, so then we get another function. So
for all
the function which takes, and then it gives back a B. So this B needs to be the goal, I suppose.
Yeah, the B should be that thing after the comma, isn't it? And the exists.
No, so I think the A here. So we pass in this thing. The A is the left-hand side of the pair. And then this PA is the right-hand side of the pair. So the left-hand side of the pair is the thing which is the subject, and then the PA is the actual property that the A satisfies, and then we have to give back a B given that. So we do the elimination. How will that help? So we'll get some list Y's prime, and then this Y's prime concats Y's equals the singleton Y.
But I'm wondering why can't we assign that?
Well,
Don't know how to synthesize argument.
yeah, we should be able to assign it.
Okay. Let's do a little.
I think we need to pass it. It's like a continuation almost. It's like continuation passing. You pass it that hypothesis, and then you pass a continuation which accepts the.
Oh, here.
Yeah. See, it's a function of two arguments. It's the thing on the left-hand side of the pair and the thing on the right-hand and the property. So that W is the list Y's prime, and then the underscore is the property Y's prime plus Y's equals Y that it satisfies. And we need to return a proof. We need to return the goal.
Yeah,
The goal.
I'm definitely struggling. But if you know what to type here, let me know.
Yeah, so it's that.
Because I know Y's prime
I think it
is empty.
I think it's this. So it's this H2 argument. So we need to pass a function. So on line 282,
yeah,
we have to pass a function which accepts the list which satisfies the property, and then the proof that the property is satisfied, the two arguments. And the return type is the B, which is the return type of the whole thing.
So we have to show
The goal.
this one. X equals X.
Well, the goal of the whole thing.
And yeah, no, okay. Not this goal.
Yes.
No, yeah, no, we just want to.
So what are we doing? We're extracting out the two components of the pair, the left-hand side and the right-hand side of the pair, and they get passed into this function we provide. So the arguments to this function are the components of the pair. So we eliminate H. H has two components, and they get passed into this function.
I was wondering if we can just go. I have this exists, right?
Yeah.
I just want to say Y's prime is the empty list. And given the
we don't get to choose. It's some list, but we don't get to choose what it is.
Okay.
There exists some list which satisfies this property, but we don't know. We don't get to choose what that is.
Okay. Well, we do know.
That's my understanding.
It's not the left side. We have to do that.
Yeah.
Sorry, I do know that. We can't apply it yet, or can we? Like we could do like we did before. Oh, that's convenient. Can I do this? No, okay. And I can probably do this. Is that the same as? What's the difference? So, okay. So we have to use it with the goal like we did now, right?
What does the goal look like before you apply it? I'm not sure what it did to the goal. Oh.
Before. And now we have this, so we can intro H0. through H1. Yeah, now we're back to the old goal. But we have, yeah, we basically have Y's prime now, I think. This would be
Hmm.
yeah, Paul, do let me know if I'm missing something, and because I am definitely not. Yeah, if there's something you want me to type, like, do let me know.
Yeah.
Like,
I don't know.
I
don't know either.
okay, good.
Yeah, I'm also reading up again on existential quantifiers. It's been a while. That
Yeah, it's been a while. Yeah.
hypothesis 1 looks so weird. With underscore pys, but then pys is like doesn't
appear on the
appear
right
on
hand
the
side
right
of the
hand
pair.
side. Yeah.
I'm just wondering. I feel like in coq we could always just destruct and exists, like every time. We just go.
Yeah, let me try and paste this example to you, because I think the lint does destruct it, but you can't. It doesn't just give you the. It's like a continuation passing. You don't get to extract. But where should I send it to you?
In the Twitch chat. It's good.
The Twitch chat. If we look at the actual documentation of the existential quantifier and that they're improving in Lean, I can't link to the actual example, but if you scroll down a bit, then you get to a section on that uses a lim.
Okay.
Exist.elim. Yeah, here. Exist.elim performs the opposite. It allows you to prove a proposition Q from there exists X PX. So what you do is that H, you have a pair of an X and then a proposition. And so what you do is you pass that function which takes those two arguments. So in coq we would do destruct and we get the W and the HW.
Yeah.
But here it works differently. You get them passed into a function which provide like a callback.
Okay.
And then you get to prove the goal inside of that function, given those two arguments. What's weird in our situation though is that we have two things on the left-hand side of the pair. We have this Y's and then we have this underscore business.
Yeah, we want to repeatedly call exists. Like we want to go, okay, we know it's this, and now we know it's this.
In the next section 5, there's also they also talk about the exists tactic. Maybe we can use that.
Oh,
okay.
Yeah,
that would be better.
If you on the left hand side, you can go to the next chapter, tactics.
Yeah, this works in the goal, I think.
Yes. Oh, hold on a minute. So we can use cases. There we go.
Yeah, destruct.
Oh,
Test
yes,
cases.
yeah. That's what it's basically doing.
Yay, okay. Cases H
Great. With intro.
And then, yeah, it was an intro. And then we had
the pair.
Y's prime and there's a C. Yeah, cool. That was right. Is that what we
see? The thing is, what's weird, we have two things before the comma. So I'm not exactly sure what that means.
Okay. Well,
it's like a nested exists. So,
No. Yeah, they do
what's
cases
wrong
on
with
it
the
again.
Yeah, yeah. So what was the?
I think it's normal.
Well, I mean, in that, yeah. No, but in there, because the cases has two meanings. So the first case is for exists, and the second case is for the disjunction, or the
Yeah,
conjunction. Sorry,
yeah, yeah.
but we have some weird thing going on. But we need to do it twice. We need to cases of the underscore pys.
Yeah, let's see here. Yeah. Yeah, we have well, one exists.
Yes.
We could we change this? Like to be. Then we have one exists.
Yeah. What does what have we written there? Why do we need to do that?
Okay, let's go look at the cock.
Yeah, because it's odd.
Yeah, so there's just a copy paste. But yeah,
Yeah.
we do use it. Is this just going to be
Okay.
equal? Yeah, and then
So it's fine then. It's just that usually it's confusing me because in an existential quantifier, you usually have a pair with with a thing and then a property, but we have a thing, a property, and then another property on the right hand side.
Yeah.
It's fine.
Yeah, that's getting into, so maybe we do. Can we do that? No.
No, I think you're right that it's not an underscore. It's like we need to do a cases on that underscore pies again to actually get, because we can see it on the right hand side. I think what it actually.
Yeah, okay, that's proper syntax. Okay.
Yes.
Okay, now let's see what py.
And this thing has a part has the property on the right hand side that we actually want.
Yeah.
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 That's the actual property.
And then
this goal looks so much more manageable.
yeah. Yeah, we just needed the proper destruction. But yeah, oh yeah. So I think that's kind of what we want with we want list app uncons to do a bit more work for us here. So and that's kind of what we did here, right? We applied it and we destructed, we did some substitutions. And then it kind of helps you a lot more than just applying the theorem. So we're going to move, once we prove this, we're going to move some of it back up into the tactic. But yeah, let's first see what we can do here. Yeah, so we have two properties. It's kind of like px's and py's. And yeah, so that we know that. Okay. So okay, this has to be the left side, right?
Yes. Oh, hold on.
Yeah, because y's is going to equal y's. Oh, sorry. But we haven't given anything, and there's no way.
But y's prime could be singleton y, could it? Yes. Then
then we have x is equal
Oh,
to,
then it wouldn't work. Yes, yes, yes,
Hmm.
indeed. Okay, yep, left it is.
but something is weird. Okay, now, yeah, we need, yeah, we need something.
No, we're missing a constraint somewhere.
Yeah. Yeah, we definitely lost something.
Yeah.
Is sub the thing? We rewrite. Yeah, we definitely lost like the ability to give y's a value, right?
Mm-hmm.
We just look at the cock here. Oh, list single. Oh, interesting. Okay. Let's see here. Let's just see what happened. Nothing. Okay. Right. But given list single,
Yeah. What is this single meant to do again?
yeah, it just does things with single lists. So it's yeah. But list app uncons was already more powerful in this case already. So
Right.
is there anything else we could destruct here except? Well, x's and y's are currently just variables that can be destructed. Yeah, but there's nothing here to suggest that it would do that. Yeah, it takes this. And it breaks it into the condition and the exists.
Yeah.
That's the C and E. And then we have these two cases. But for each of those, that's the semicolon in cock, it destructs oh no, here, okay, it does one for the one thing, one for the other thing. Okay, so the first one, it just does inversion on the condition and substitution. So that would be this, which is, yeah, basically saying destruct it into x equals the empty list and y is equals this, and then substitute it everywhere. Like that's all it's doing. Where on the exists, it breaks it up into the second exists, the E0, and then it breaks up the second exists, which is what we've done, and then it substitutes it everywhere.
Mm-hmm.
So that's what this line is doing. So it is doing what we've done here. We're doing everything right, and then it just substitutes the hell out of it. Now, I don't know. why our y primes is so. I mean, if we can do cases on y primes, right?
Mhm.
Yeah, because it has to be the empty list, otherwise it wouldn't work. So
So if we're in this case, yeah, we can see this is all good, and we're going to be able to prove the left side. But if we're in this case,
we get a contradiction.
yeah. But I guess then we also prove it. Contradiction is good.
Yeah, that's good enough.
Like,
Yeah, I'm not sure
But then we
whether
have-
we're losing anything. Like
hmm,
there are enough constraints to prove it.
So in the cog code, was there a discriminate anywhere?
no, no, no.
Maybe in the constructor,
Yeah, maybe.
there's some discriminate there because it knows it something can't be true.
Yeah,
It's magic.
yeah. So why is this a pretty bad name? I don't know if we can.
Yeah.
Call it something else. Z's, I guess. And then just here apply the left side. Then simple sum pyx sump at in
In. Oh dear.
at, yeah,
Yay.
okay, and then yeah,
With and
rewrite,
without. Yeah.
or yeah, and then
Isn't it apply and intro and then
yeah, I think it's exact.
oh
Like
yeah.
yeah, but let's just go. I just want to see this actually.
Mhm.
Yeah, cool. Yeah,
Hmm.
okay. So that would have been, actually I prefer that. Okay. Cool. And then this one. Is it a contradiction? I don't think so. Yeah, we want to
Oh
be
yeah, I
right.
forgot about the other side of the or.
See, this is not a, there's no contradiction here. We just can't prove it. Hmm.
Well, z must be equal to y.
Yeah.
Hmm.
And we're already screwed. Yeah, z is equal to y. Z is the empty list. Y is the empty. Actually, oh no. Yeah, that works. Yeah.
Yeah, we just
Yeah.
do cases on more cases
Hmm.
on z's, I think. Well, or yeah, or on y's. I think on y's makes more sense because if it's empty, then we.
It has to be empty, like this.
Yeah. If it's empty, we can prove it, and if it's not empty, well, then we have a contradiction.
So this is where list single is going to help us. It broke it up for us, right?
Oh, nice.
And then we know it's this one. This. So we just did this. Is that or that? And I know it's that. Okay, that's how you do it in the goal. Oh, it isn't. Yeah, it is an or. Oh, we can show this is contradiction. Yeah, that's how. Okay, we have to do cases and do both sides. Not intro. I think it's. All right. Yeah. Okay, that's the syntax. Can we call this PYs again? Yes. Yes. Okay, great. I don't have to think about another name. I think.
Well, we've got a Y's is Y and a Y's is empty.
Yeah, the goal is why is empty, so that doesn't help us, but we know this is a contradiction over here.
Yeah, but the second part, the
But
right
the
hand
second
side
part is Y's is empty Y.
that's the easier
PYs.
contradiction.
No, but this is the goal, so it doesn't help us prove a contradiction.
Oh,
Hold on.
oh, I see what you mean.
Only this helps us. Because it's an hypothesis that says the empty list is equal to something that's clearly not empty.
Yeah, don't we have a theorem like that?
We have a tactic for that, but we do need to break this up. So I think we just have to go have py's prime equals py's dot left. Yeah, and now we can just do list single. And it will should have done it. Oh, list empty maybe? Yeah. Okay. So that's kind of annoying.
Go back to the previous bit. Lost the thread. So why is it so in the PY's proposition?
Yeah.
It's saying something on the right hand side. It says Y is equal to the empty list Y.
No, it doesn't. It says Y is equals to the singleton Y in PY.
Sorry, the singleton Y. Sorry.
Yeah.
And in the goal, we have Y's is equal to the empty list.
Yeah. So we cannot use PYs to prove the goal. So it's useless information. But on the other
What if
side,
we used it? What if we used to prove the goal?
So on the other side, the left side, we get PY's prime, which says that something const to a list equals the empty list. And that's a contradiction.
Yeah. Got it. Thank you.
And that's what list empty is doing.
Yeah.
And now on this side, we need to show that Z's is the We now have y is equals empty list, which is good.
Mhm.
Now we still need to show z is equal to y. Z is equal to y, and z's is the empty list. We still need to show this.
So I guess we have to do again have yeah, exactly. And then we can rewrite pyx axis with that pys prime. Then we substitute
Ooh.
z cons z's with y.
Yeah, yeah. Oh, that's nice. Yeah, that's very good. Okay, okay, let me figure out. Okay, so rewrite py's prime at yes, pyx's. Yes, nice. Okay, and then now we have our two assumptions, and we just need to break this up. So apply end at intro and assumption. Boom.
Nice.
All
Yeah,
right.
this was longer than expected.
Yes. So that's a pain, right? That's the pain we want. We want to make this proving something like this much easier using our tactic.
Yeah.
That's kind of what we want to do. But maybe let's take a 5-minute break and then come back to tackle that.
Perfect.
Cool.
Okay.
Hello.
Hello.
Hey,
Hello.
and we're back. So, yeah, we have this long proof. You want to see if the tactic can help us make it much shorter. This is what we did in Coq, and it achieved the proof in 6 lines. Now, yeah, let's see how close we can get. The first thing here is we applied the theorem, which we also do here. So step 1 complete. Then we want to destruct. So once we've applied the theorem, we get this hypothesis. And we want to say, given it's the left side, do something. Given it's the right side, do the other thing. Yeah, it's interesting. Because in Lean, we just do cases. And I'm kind of wondering if that is actually going to work. But so maybe we have something that's already working, right? So maybe we'll just leave this as like a reference.
Yeah.
And then I'm just going to create the tactic again and just call it uncons 1. And then I can call uncons 1 here, and it's all working. Okay. Now, I think we can just run. Oh, I really don't know if this is going to work. But what I want to do is run tactic cases name. I think this, yeah. So this is like a cast function. It just says name is actually of type ident, and then cases can take it. We do this. It does do something. Yeah, that works. Now it's a bit irritating because it doesn't give it a name, right? It split it, but it didn't give it a name, and we kind of.
But isn't that because you used bullets? Like otherwise you can name it instead of giving it a bullet.
Okay, let's see. Yeah, no. So it's expecting another command, like the cases with. Oh, well, okay, we can type with, but now this is incorrect syntax.
Yeah.
Maybe there's something here. Where's the book about cases? Cases with, yeah. Yeah, so this is the version we're using. Okay. I don't see anything about naming it. But cases with. So yeah. This is another way something gets destructed in the goal, and then you do get some way to give it names. So I'm wondering, it is an or, right? So let's just take this back a second. I guess we could just go apply. No, okay. We're just gonna leave this here for a second. Okay. So if we're here, can we do apply or dot intro? In H. Okay, how does apply in work? Okay, yeah, this is the apply in is kind of fun. So maybe let's try using it here. Apply in name or dot intro, and okay, fair enough. No, it's not gonna help me. Or dot ilum. Okay, maybe that's what we want. Or dot ilum. And then no.
What did you do?
Nothing. Okay. Let's or okay. Or the lim takes an or. Yeah, we have that.
And then a function to tell you what it does on the left and the right. If we apply it, give it a tactic, hypothesis, then it gives us two things, just what we want. Yeah, is it what we want? Not really. No, it'll give us back a function. Like we give it that H. Then it'll give us a function that takes two arguments, left and right.
So, okay, there's another way. It's I don't want to do this, but so we will run this. Whoa, we run this cases thing, and then we run rename I, and
all this magic.
Yeah. And actually, wait a second. When we get here, right? We had something called H. We can reuse the name. We don't need a fresh name.
Clever.
So we should be able to go name. Okay. And then yes. Does it work? Yeah. Yeah. Okay. Wait. Okay. It worked for the first one, but no, it did not work for the second one. Okay. Can we do this? So basically rename H on everyone.
Mhm.
And if we do that, yeah. Yes. Yes.
Woo.
All right. Okay, that's good. That's good. So now, yeah, we don't have to do this. So we get here. Yeah. Okay, so we've made progress. Okay. Over here, it thinks we can use the single, but I don't. No. Okay. We need to do some more work. So we've, yeah. What we did is we did the first breakup, right? That was good. Now we want to do the breakup for exists as well.
Mm.
And we only want to do that in the second case. Well, that's where Coq has these square brackets to show like we're tackling the first case or the second case and only apply these tactics there. So we want to say only apply these tactics in the second case. Now, there was tactic combinators thing here, yeah. So for example, this says apply the next things in every case.
Yes.
All goals, oh, any goals, yes. Yeah, so you could do this. It's okay. It's like basically does try on every goal.
It will only match the second one.
Yeah,
Is that the idea? Right.
we could do that. It's not
Mm.
exactly what we want, but yeah, everything doesn't translate perfectly. So we could say run any goals. Yeah, like this. And then we want to do 2 destructs basically, right? We want to do, it's also H again, so we can still use the same name. Okay, it kind of worked in this case as well, which we didn't really want. Yeah, we didn't want that. We didn't want that. But it's okay. We can still use match. We want to get the hypothesis, the new hypotheses for H. So let's just see. I think we can build something, get hypothesis, which takes a string. This is the H name, and we say if H name equals name, return type. Return none. Is that a thing? We don't want it to be an array, we just want option, maybe. Thing.
Yeah. String and ident.
Okay. This is ident. Okay.
Ident. Can you?
I can make this.
You haven't declared name, so there.
Yeah.
Oh,
Not ideal, but I think. Just building and reloading. And this might not work because of the context, maybe not updated yet. But let's see. Get hypothesis name. New hire.
Cannot be mutated.
Okay.
Interesting.
This is fine not to mutate it. You just does sorry. So if it matches this, like it solves everything, right? That's going to be our little taste. So we want to match an exists, and only an exists. Oh fuck.
it will be tricky with the two variables we quantify over.
Yes. Okay, I just put a random pattern here just to see what's going on here.
Yeah. The matter that is an option. Optional. You bind new hype, and then new hype isn't optional.
Yep.
Right.
Yep. Yeah.
So you need another match, maybe. Like, is it
Yeah.
summoned? None.
Oh, not return. We want to throw. Okay, fine.
Good enough.
Yeah. Okay. Whatever. Sounds good.
Does something.
Okay. What's this problem?
So what? Why are we?
This is the only occurrence.
Binding.
Oh, maybe. There we go.
Oh.
Yeah.
Interesting.
Okay. Okay, we're just returning at the moment. Okay, that's a bit of a problem. We do need to throw some errors at some point. Okay. that's not what we want. We want sorry, and we do want this to be different. That's not good. Lists here. Okay. Exists some eggs. Yeah, what okay. Luckily we have this one. We have exist something equals something.
Mhm.
So we should be able to match exists yp what's wrong, expected comma.
You have to put a comma in between, I think.
That's good. Unexpected explicit.
Blah.
That's nice. Maybe another brain. No, okay. Yes, a thing, comma, a thing. Okay.
So binder.
Ooh.
I'll try putting a space before the comma.
Yeah,
No.
okay. No. I'm wondering this QQ library, quote 4, I think.
Yeah, it's quote 4.
Yep. But there we go.
Wow,
That
there are
was-
no dollars though.
Yeah, that's fair. But
Huh.
More dollars.
It should be possible. Okay. Whoa. Okay. What?
Maybe just a dollar before the P. Huh.
What?
So why is this working now?
Let's see. Okay, what's the problem? Has not been implemented. I beg to differ. It just uses sorry. That's fine. It has not been implemented. Okay. Okay. What a. Okay, it doesn't like sorry. Okay, that's fine. There's a way to print things, so we can just print something. Okay, that should be good. And come on.
Maybe we should also print something in the other case, just to see that it's printing at all
Yeah,
in
cool.
the default case. No, it prints no.
All right. Good. And maybe you can add the name. No, it won't help. Won't help. Okay. Cool.
Wow, this is like imperative programming debugging.
Yes. Yes.
Well, this is how you debug Haskell.
Yeah.
Yeah, you try. You try.
You try.
Okay. So we're matching exists. Oh, we're not matching exists. Okay. Now, I actually want to know. Oh, we're printing no, which means.
Yeah.
Oh no.
Maybe we need another case with two things before the comma. So exists x, y, comma, $px.
Okay.
Still printing now.
No. But yeah, I think that's more on point, right? So what if we can do that?
That's cursed.
No,
we can't. We can't. Okay, what is this problem?
Maybe y was not a good name. Oh no, but you yeah, because you used the y there as well. But we had
Resulting terms contains meta variables. Okay. That's what we want, isn't it?
Yeah.
Let me error messages say that.
But
Error
also,
messages, yeah, the term is exactly what you want. Error.
also, like, we'd be happy to match anything.
Did you try p with
What?
one parameter and but two variables before the exists? Because that's what it looks like, the thing we want to match, isn't it?
Yes. X and Y and then P of X.
Like this.
Yeah, that's what I thought, but it's not working.
Okay. Unknown identifier. Yeah. Okay, but we know this is a thing. So let's see in this library. Yeah, here's one. This is kind of exactly what we're looking for. So almost.
Except that we don't have p, x, y.
Yeah.
Yeah, because annoyingly the Y argument is not used in the right hand side.
So if we can't we also print the new hypothesis when we print no, so that we can see what it looks like?
We can try.
That's what it looks like.
So that so that's this one. It's not actually looking at the next one. So that's oh, what the fuck is going on? Yeah. Mm-hmm. Yeah, so this is only looking at the first thing. That's why we're only seeing this. Understand, like, because we're only looking at this case where, well, I say that, but
So we would need like a all goals or something.
also, actually, what's also happening here, H has not been updated. Yeah, so it's using the old H, plus it is only looking at the first one. So we have two problems. So the old H is this thing. So we can ask run, we can look at run.
So do we need to call like get context thing again? I can't remember what it is now.
Yeah.
Get context.
Maybe this.
And then do.
Yeah, that did it. See, now no is showing both. So now, yeah, we still have the second problem, which is we're only looking at the first one, we're not looking at the second one. My thing is, let's make a tactic that just breaks up exists, just does that.
Yeah.
Or wait, we should call this rec exists, right? New tactic. Okay. And it just does all these things. Then we probably don't need the new tactic part. And we do. Oh, fuck it. Let's loop through all of them. We're gonna wreck any, like.
Yeah.
Okay. And so then we say any goals. Yeah, no, yes. Yes.
No, it is matching that pattern. That's encouraging.
Yes.
Yeah.
And now, very encouraging. Yes. Yes, very encouraging. Now, yeah, we can break it up. And I think we can do it twice. We get this first thing that is not broken up, which is great. Get the second thing that has the new H, yeah, without the exists, it's totally gone. And yeah, we have two really badly named things. Now, what did we do for naming buckle? Okay. That's
Rename
great.
I, wasn't it?
Yeah, but in cock we
So
did
in cock,
like no, wait here. Yeah, we called the one E and the other one E0. Great, excellent names. So there's this thing, we go fresh or make hypothesis. We give a suggested name and a tactic to run. I wonder if this is going to work in this case. Well, I don't think so. I think we need to do the manual thing, this fresh. Yeah. So fresh E. And E0. And I think in this case we can just do plain. Oh no, okay. E. Yeah. Maybe in this case E0. Oh, dollar. No, not dollar.
oh, what?
Yeah, dollar name. Yeah, dollar.
I didn't.
I did. Okay. Okay. Cool. And then when we get here, yeah, that's okay. Right? E is a bit weird for the first one. What about maybe small e and big E? I think, yeah, that looks slightly better. Okay. So we have done the deconstruction part. Now I think we just need to go rewrite everything as much as you can. I think all goals rewrite sunk. I think at least we want to also break up any ends. Like I think
Yeah.
that would be really helpful. And we have something. We don't. I was working on something for this. At the moment, we have this, which we can just do. Rec conj. Well, it's kind of a copy of this first, and then this. And yeah, and we don't need these prints anymore. Just rake all the conjunctions. Yeah, so we've got our
Nice.
exit. And then we want, let's see if this now does anything.
Oh.
No, nothing. Sorry. But we just want to go rewrite everything with everything. So I'm just going to check if we have any RWs here. Like we usually go given something, rewrite everything. Yeah. So we can do that. But I wonder if there's a tag like rewrite star.
Yeah, that would be nice.
Let's see. Subs.
Do they have like a subst tactic?
Yeah. Subs. And there's also this file. Subst. Is not what we want.
No.
There's simp star, just as you wrote RW star, so maybe that works. With star in square brackets.
Yeah. Nice. So. Okay, so then our first, it solves the first goal for us. We don't even need to do anything. For the next one, yes, great. We need to break this up. That's a step we want to do manually. So what was that? List single. Maybe that was the list single. Yes. Look at that. Look at that beauty. Oh,
Nice.
and, well, I guess it's just assumption, but
yeah.
And okay, let's just.
I love how it says "what" at the end.
No, yeah. But let's just imagine this was slightly more complicated. Then we would do apply cases H. Yeah. And then we would do yeah, this. Come on, get up. Come on. Oh no. You tried. We were too smart. Yeah, then it should be just that. Cool.
Looks so much better.
Yeah. Now, right, let's just do one more. I just want to see like how well, like the tactic is supposed to compose well, right? You you want to be able to just keep going with this. Okay, so same idea, just more combinations. And we're just gonna go list on. There we go. Interesting. It solved the first one, right? I think it even solved the second one. X is gone. X. Like it's even removed X from the equation.
How did that happen?
Yeah. So actually now we're pretty much. Yes, great. Look at this. Oh, beautiful. We have exactly the previous theorem.
Yeah.
After applying it once. So we can just apply it again. And do less single and assumption.
Nice.
Nice.
Yes. that is composition. Like that is so good. Okay, so we could just rename this to the original and delete all of this.
Yeah, I think this is like the first good advert for tactics we've had in Lean so far.
Yeah. There we go. Boom.
Very nice.
That's a very good place to stop. I cannot believe this worked so well. I like that was.
Yeah, I was a bit afraid like that a whole new mission would start here.
Me too. And it's just like, oh, beautiful. Oh, great.
That's so satisfying.
Yes. Yeah, we did it. Wow. So the only thing that's left for a list tactic is like a bunch of proofs about not. And then just to combine it with these ORs and a repeat. Like we just want to combine list app uncons and list app and list single and list empty. Like that would be our ORs. And then, yeah, so it would just be like run tactic, repeat, first, list empty, list single. So maybe let me just write it out quickly. Because I'm not going to be able to resist to do this on my own time. Like, so let's just get it on the screen. And we just say ballistic. So yeah, would just be this and the list would continue.
Right.
Isn't that
doing it for me?
Like how inefficient is that? I mean, when we just try everything as often as we can, like it seems a bit risky that we get stuck or like it just takes very long.
Yeah, so I think so list app uncons is like something where you want to kind of make sure you're not just elaborating forever, right? But if you look if we look at the theorem, and see, it will only apply it in the cases where there is a specific cons.
Mm.
So it will elaborate, but only if you have like specified a list. So you would have to say like, okay, cons, but you will usually only have one cons or two.
Mm.
So it will only do that small thing. If you do like with these tactics, if you do like ring type of stuff, like where you have ands and ors and you're like just swapping them around, and this tactic swaps it the one way and this tactic swaps it the other way, then yeah, you don't want to do this.
Yes.
So you want to then use a ring tactic, a tactic specifically made for that case. So cock has like a ring tactic. So you specify the properties like that you are a ring, and then you just go, please figure out that these two rings are like equivalent, and yeah, it just does it. Yeah, there's like a set weight ring package that does it for you. In this case, for lists, I think we also want to bring in like a SMT solver, and I think we can do it. And there's they're working on an SMT package for Lean. It's still under construction, so we'll like probably not use it until it's ready, but later we would just want to throw that in. And until then, we kind of just have to make sure that our tactics aren't going in circles. Yeah, but it's definitely something to watch out for. Then, is it efficient? No, but it is more efficient than my brain.
Yeah,
That
you're trading certain CPUs, human CPU for machine CPU.
Yeah, and what it does is not actually that expensive. So it like does some pattern matching on the hypotheses, and then applies some tactics, and it tries to do some rewrites. And we don't have an infinite number of of these theorems, so you're just worried about the case where it will keep on elaborating. Yeah.
Okay, so it's like not really efficiency, rather like something like a what do you call that in concurrency again? Like a deadlock sort of situation that we have to worry about.
Yeah, and yeah, we can easily spot those with lists. So
yeah,
not easily, but like easy enough.
Yeah.
And yeah, it's not efficient, but it's not expensive enough that we need to worry.
Yeah,
like it's still pretty cheap,
and it won't necessarily generate the greatest Lean code, but you never see it.
Yeah,
so.
the readability is horrible. Yeah, if you
look at the underlying term, yeah,
if you afterwards go like, oh, apply the tactic, let me just read the proof. The underlying term, you're gonna die. Yeah, let me read the AGDA for this. Like, no. No. But at least you didn't have to think about it. So, so yeah, I'll probably just where is it? I'll probably finish this. Well, I finished it now. There it is. Like, now we can only iteratively improve it, and write a bunch of theorems here below that use it and test it. So it's not as interesting for streaming, but we might do that next time, like depending on how much time I had to do anything else. Yeah, but this is the gist of it. Like that, this is, yeah, the rest is just cleanup.
Nice.
Yeah, I'm gonna stop the stream. Yeah, thanks everyone for watching.
Yeah,
And,
thank you, viewers.
yeah, hope you learned something. I know I did.
I definitely did as well. It's not too bad, that Q library.
No, the Q library makes
yeah.
huge difference. Like, I'm so happy it's implemented. Like, yeah, we wouldn't be able to do any of this without it. Cool. Bye, stream.
Bye.